So yes, I'm going to be talking today about feedback, and particularly about the forms of feedback and how we regulate star formation in galaxies, and how we might use high specific energy and low mass loaded winds to regulate star formation. So kind of a brief summary of galaxy formation so far in many models is that we have a nice little galaxy, and gas accretes onto this galaxy from the cosmic web, whether it be filamentary, whether it be cooling from the CGM, whatever, it's coming in, and then a small fraction of the gas that's in the center, gets into the center, forms stars. And a byproduct of this star formation is feedback. And this feedback then, in the kind of the classic model, then chucks out the remaining gas and out into the CGM, so you stop forming stars because you don't have any left in the galaxy. Now, the kind of outflows that you get in this case, we characterize them with two parameters. The E to E here, the energy loading of a wind, and E to M here, the mass loading of a wind. So this is just the energy and mass outflow rates normalized by the star formation rate or the energy from star formation. Now, turning first to the mass loading. Now, a lot of simulations, particularly kind of the larger scale ones, they've been calibrated to try and reproduce certain observables, particularly in the case of the stellar mass function, among others. And what tends to happen in many of these models is that you end up with reasonably high mass loadings, I will say at injection at least. This is what the mass that you're taking out of your ISM and chucking out. It doesn't necessarily mean that at larger distances that is what the mass flow rate that you would measure would be, but at injection, then with reasonably high mass loadings, particularly in low mass galaxies. And now this is this classic ejective feedback. The stuff has come in, you don't want it to form stars, therefore you have to throw it out and get rid of it. But I'm going to be talking a bit more today about this other parameter, E to E. But there's been hints from various idealized models and semi-analytic models and from observations that mass loading is not all that's cracked up to be, and that there's a hot diffuse phase that doesn't have a huge amount of mass in it, but could be quite important in regulating star formation. And there's been interesting work, particularly in the past few years, about this CGM heating. And now, because these hot winds, because this is high specific energy winds, these are a high temperature, but not much mass, they heat up the circumgalactic medium, and they do still expel gas. But this is not ejection from the galaxy itself, outside of the ISM. This is ejection of the CGM. You're pushing out gas far beyond the virial radius. And so you halt further inflow, and so instead you regulate in a preventative way. You stop gas getting in the first place, rather than everything coming in and going out again. Now, modeling this has been fairly difficult to do with these high specific energy winds because they are inherently diffuse. But with a scheme that first developed by Matthew Smith and also expanded further by myself, we've called Arkenstone. We've been trying to do just this. The full scheme has basically you launch winds in two phases. You have a hot phase that is fairly low mass loading, a high specific energy wind that you use to heat up the circumgalactic medium. There's also a cold phase, which is these subgrid cold clouds that are launched and accelerated by the wind because they interact on the fly with the hot phase. And these can act as a bit more of ejective feedback. But actually, in this talk, I'm going to not talk about the cold phase at all at this point. This is a hot phase session. So actually, I'm only going to talk about this hot phase and how you might be able to regulate star formation using only this hot phase preventative feedback. So just as a kind of a thing here, so we have on these two Milky Way mass halos, starting from redshift 1, because this is where I decided to switch the wind model over. So this is starting from the same point. On the left-hand side is the Auriga model, which is kind of a bit more typical. It has relatively high mass loadings at injection, at least. So stuff comes out, comes back in, and there's this recycling going on. And then on the right will be the Arkenstone model. And there are a few differences that you might notice in what is happening. Now, this is relatively high energy loading on the right. I'm not saying that this is exactly what's happening in all galaxies. But what you can see on the left with the Auriga model, there is stuff that comes in and out. There's kind of stuff thrown out to reasonable distances, but the cold gas is all still very present around the galaxy. In this case, you're really heating up the CGM a lot more, disrupting the inflows and really destroying a lot of the cold gas that's in the CGM to start with. And you end up regulating star formation in quite a different way. Now, this is just kind of pretty visualization, but we've also run this in 25 megaparsec cosmological boxes so far. And it looks something like this, some results. So, redshift 0 stellar to halo mass relation. This is one of the classic things that people, simulators look at to go, are we anywhere near what the real universe looks like? And what we kind of find here, so just to draw your eye, the dotted line here is an observational inference of this from Shunter-Vattel 2022. The solid black line is is almost a fiducial TNG model. It hasn't got magnetic fields in it for reasons I can go into later if someone's interested. But then what we do is just replace the star formation stellar feedback model and within this and carry on. So it still has the same TNG AGN model. And so particularly because of the small box and because of that, this high mass end, I'm not worried about too much at the moment. We're kind of looking at the lower masses. With these energy loading parameters here, you can see that the amount of stars that you have varies quite strongly with the amount of energy, the energy loading that you have in your winds. With a lower energy loading of 0.1 here, we're massively overproducing the number of stars in these low mass galaxies. With 0.9 at the other end of the scale, we're actually underproducing stars across a lot of the halo mass range. There is a sweeter spot in the middle, which is closer to the observational inference, perhaps still a little lower, around 10 to the 12, and perhaps still overproducing stars at the lower halo masses. But this is using preventative feedback. The mass loading of this is around 0.3, and currently for this one on the left, it is fixed across all halo masses, which is not what most models do to start with. The middle one here is what happens when you change the mass loading at the fixed 0.3 energy loading. And actually, it doesn't actually have as much of an impact as the energy loading. The energy loading really dominates, and this is one of the key points I want to hammer home here, is the energy loading of these winds is what sets the slope particularly and the normalization of this. The 0.9 run never quite made it to redshift 0 because it failed very miserably. And then on the left, on the right here rather, there's a run where we have an energy loading that scales with the halo mass. So at a lower halo masses, we have higher energy loading, and it brings us reasonably. This is not particularly. We haven't recalibrated the TNG feedback black hole model. We've kind of gone, that's vaguely looks okay-ish. Great, sounds good. How is this happening, though, in the last couple of minutes of show? This is the circumgalactic medium. Obviously, that's why we're here this week at redshift 2. For all of the same runs as I was showing before, this is the volume-weighted average temperature within the virial radius at redshift 2 for these halos. And this is kind of these are showing the median across all halos in the box, normalized by the virial temperature. TNG is consistently kind of down here throughout the thing. It's a relatively it's sort of set by the feedback model is what this looks like, and partly through just visualization. But we can see in every single case where we have these high specific energy winds, we have a hotter CGM. And that is partly, at least, where your preventative feedback is coming from. You're not allowing this gas to be cooler and to fall in. But also, looking at the gas fractions, this we see that actually a lot of material is being ejected from the CGM. It's being pushed outside of the virial radius. But remember, these mass loadings are, particularly the lower down you go in mass loading, in halo mass, the bigger the difference in mass loading between the Arkenstone runs and the TNG runs in this case. And so we're actually throwing out a lot more material, so the CGM ends up being more diffuse and hotter. And that is what regulates the star formation in this particular case. And so in conclusion, we're saying out with the cold-ish. And instead, we are going to use hot diffuse winds to regulate star formation instead. And I will leave my conclusions up. I would just stress that we're not necessarily saying that it is all preventative or all ejective. It is some combination of the two in all likelihood. But the CGM is really going to be crucial to help determine between these scenarios. So thank you very much.
Mr. Light on comment. Okay, question?
Yeah, I'm curious how you can reconcile this picture with observations of CGM at low redshift, where we know that there's a huge amount of cold gas around them, and they are all consistent with being out, especially at Milky Way-like galaxy at redshift going on. Like, can you reconcile that picture?
Yes, so as I said partly earlier, the RPSM models form two parts. There's a hot phase, a hot wind launched, and there's cold clouds embedded within this. Whether they cool out of the cold wind, we're fairly agnostic of where the cold gas within that comes from, or it's kind of pushed out from the galaxy. We haven't got that in at all currently. So it's also worth saying that we don't destroy all cold gas in the CGM by doing this. It depends on what the energy loading you're looking at is, about how much gas there is. And so, and also, as another point, do I have that slide? At redshift 0, the CGMs are much similar. They are quite similar between the various runs that are showing. In terms of the gas fractions are slightly different, the temperatures are much closer to the kind of the TNG result at redshift 0. So at redshift 0, the differences aren't as big. Now this is averaging over the whole CGM. There is a lot of other stuff going on in there that's kind of averaging over a lot of complexity. But by redshift 0, the CGM potentially doesn't show quite as big a difference as it does a slightly higher redshift. So I think there's a few reasons there for why the cold gas will still be there and will still exist. But I think the hot phase will be particularly useful to try and constrain these feedback models in the future.
Hi. It's really cool that you're able to control the energy versus mass deposition in a controlled way and address the problems independently. I'm wondering about whether energy loading or mass loading shows different behavior with respect to the recycling of the outflows, because I think that would have implications for the chemical evolution of the galaxies.
Yes, it does, and it's not something I've shown in this talk, but what we tend to happen is that if you have a high specific energy wind like this, and you just keep turning up the mass loading, eventually the wind does not make it out as far, and it starts collapsing back. And particularly when you include the full Arkenstone model with the cold clouds as well, and Matthew's paper describing this should be out next week, is what he reliably informed me. What we find is that if you have the higher mass loading in the cold clouds that are launched with it, you can end up poisoning the hot wind, and so it doesn't actually lift stuff out as far, so then it falls back much more easily, and this recycling happens. Now there is a little, the caveat is that we currently are assuming that the metals that are being launched from the ISM have the metallicity of the ISM, which is kind of a fairly simplistic assumption, which is not necessarily the case. But with this model, we can vary the metal loading depending on phase, if we have some kind of constraints from this. The aim of these was to use kind of these very high resolution, idealized kind of ISM patch simulations to infer the parameters that we're putting in this. So we can do that for metals too.
Okay, we can have one more question. Before we get that, the next speaker can come up and prepare. Yeah, go ahead.
Great, Doctor. I had actually there is a related question whether you look at mass metallicity rotation, because one of the reasons why ejective feedback is attractive is because you can get both low mass end of star scale of mass rotation and mass metallicity rotation.
I'm working on it. I haven't made that plot yet, but yes. We'll be making it soon. It will be in the paper. But yeah, that is. Yes, the amount of metals retained in the ISM is partly a model parameter of how much metals you load into the wind, and so that we'll have to investigate a little more in the future, I think. But yeah, it's something I'm going to look at shortly.
Okay, let's thank our speaker again.